So if you didn't hear before, I am out of Chapter 8 packets. When we got to 8.4, everybody cleaned me out. So if you were one of the people that had to get one from me because you forgot the other one at home, please bring the other one back in so that if somebody does forget on any given day, we can use that. This is usually where you think, what on earth were we doing in 8.4, 8.5, and 8.6 before we did these? Because we don't get to choose when the MCAs and the ACTs are given. And if you look at the specifications for those tests, they flat out tell you that you're going to be solving or simplifying rational functions by factoring. And that's what we had to see right before you took those tests. So that's the reason we're going to go back and do the rest of Chapter 8 now. The good news is this is really going to seem pretty basic today, because it's the first section of the chapter. And it's got a couple of really basic concepts in it, but we're definitely talking about rational functions. And today is about actually two types of variation. Inverse variation is the heading for this section, but we're also going to be talking about direct variation. Well, if I can spell direct variation, that would help. There we go. There is another section in the book called direct variation, but to take a full day on it would really be a waste of time, and you're going to see why in a minute. Because it's something that you've talked about since, you first learned to graph y equals mx plus b. It's very basic, very, very basic. So we're going to recognize and use not only inverse variation, but also direct variation today. And then tomorrow we'll talk about joint variation and other types of variation. So at this point, I hope you're saying, what's with this variation thing? Well, these are the most basic variations that we could possibly have. Let me give you an example. For direct variation, if you go to the dollar store, everything should be, although sometimes it isn't, should be $1. So an equation to figure out how much you can buy would be y equals 1x, because it's $1 for everything. You realize you have $10 in your pocket, you walk into the store, you should be thinking, 9 times $1 would be $9, and then I'll have tax, so I probably should cut myself off at 9 things. I mean, that's the thinking we do without realizing that that's just direct variation. Rogers Theater, for a long, long time, had this huge banner outside. $7, all showings, all the time, And you realize you want to go out to see a movie. You call some friends, and those friends say, I don't have any money right now. And you say, that's okay, I'll carry you, you can get me back later. And you get to the theater, and there's 4 of you, and you do your math in your head. 4 times 7, hey, that's 28, And you figure it out. So that's direct variation, situations that are really, really basic. Today, we're going to talk about inverse. And then, like I said, other ones tomorrow. We want to get the two really nice and short variations out of the way before we talk about the others. And this is a perfect example, and it always happens that we cover this in the spring, because everybody has yard work. I don't know if your parents make you help with the yard work, but everybody has some type of yard work. So you bought 20 bags of mulch, and you plan to spread the mulch from all the bags to make a rectangular layer that's 3 inches thick. So you start realizing, hey, I'm talking 3D now. I need to know length, I need to know width, and then the depth here is going to be 3 inches. How many square feet can you cover? Well, I don't know if you've ever been involved in these projects, but sometimes you get like 3/4 of the way through, and you're like, we're almost done. Oh my gosh, the mulch is gone, Or, Dad said I should spread the fertilizer and crabgrass preventer, because that's what goes down right now. And you get almost done with the yard, and you realize, I don't have enough. And that's really frustrating. So you want to be able to purchase enough. After this section, we can come back if we have time and take another look at this problem, but that's really what this is used for, is those types of situations. So what we're going to cover today with inverse variation is different than direct variation, because with direct variation, you go into the dollar store, you buy more things, you pay more money. As one goes up, the other one goes up. Inverse variation, the essential understanding for this If a product is constant, a decrease in one of the values, one of the factors, has to accompany an increase in the other one. So we're going to see some really good examples when we get to the word problem-y stuff today about situations with inverse variation. But I always think most basic one would be, if you're in a stats class, you know that you have to collect data at some point. And if the weather starts to warm up, you start counting the number of people wearing jackets as they come into the school. Well, as it gets warmer outside, as the temperature goes up, the number of jackets that people wear are going to go down. That's an inverse variation relationship. So, direct variation is the really basic one. And my hope is, when we get done today and you go to the homework, you've got two little equations in your head, and this is one of them. Direct variation, y equals kx. That's the basic dollar store movie theater. But inverse, some books just call it indirect variation. That one has division. Y equals k over x. As one goes up, the other goes down. So this is the second one here that we need in our head by the time we get to do the assignment. So direct is just, hey, y equals kx, multiply it times something. Indirect or inverse is y equals k over x. What's up with this k? K is a number that always shows up. For the dollar store, it's $1. For the movie theater, it's 7. Those numbers are always there. They're the constant of variation. Now, like it says, k is not going to be 0. Because if it were, this would just say y equals 0, and that's a horizontal line, and there's nothing interesting about that. Now, what's going to happen is they are going to give us some tables. And they're going to say, is this direct or is this inverse variation? So here's what we're going to watch for. If it's inverse, so y equals k over x, the tables that they're going to give me don't have k in them. They have x and y. So I need to figure out how x and y are going to work together. That would mean they need to be on the same side. So I'm going to go ahead and multiply both sides by x. Now, here's what's interesting. Inverse variation uses division. Y equals k over x. But to step back and say, well, what am I going to see in the data is actually multiplication. So if we take the x's and we multiply them by the y's and we always get the same number, that tells us it's inverse variation. And what we're getting is k. Now, the other thing that's interesting about inverse variation, come on, Blue. Oh, goodness. Why do I expect Blue to play nice? It never does. And I think it has to do with the fact that I don't use the green anymore because green doesn't show up for our Google meters. All right, I'm going to solve that for x. Well, we could slap a 1 underneath here and cross multiply. xy equals k. And then we could divide both sides by y. And that shows us that whether or not we solve this for y or we solve it for x, it's going to have division. That's what inverse variation does. It has division. Now, we like equations that say y equals. So we're going to stick with this one right here. Y equals k over x. And that's because we're used to that. When you think about slopes and all of that, that just made more sense. Now, when two quantities vary inversely, as one increases, the other decreases. And like it says, proportionally. But we have to figure out, are we talking about direct or inverse? And then we have to find k. And again, k is that constant of variation. So that's our job. That would be like you go into the movie theater and you're the one that's paying again, and the people behind the counter say, that's $42. Well, you could quickly do 42 divided by 7. Are there 6 of us? Oh, yep, it's going to be $42. So it's kind of that backwards thinking, but we need that k, constant of variation. So two little equations, y equals kx, y equals k over x, and then the knowledge that we have to figure out what k is and put that in. Anybody need more time? Because I see some people writing like crazy. All right, away we go. So it says identifying direct and inverse variations. Is the relationship between these two, is it direct? Is it inverse? And believe me, there's a whole lot of them out there that are neither, so they might not fit the two little examples that we're talking about today. And then, if we figure it out, make sure to write it. If it's a direct variation or an inverse, write what it is. So, direct variation starts as y equals k times x. Anybody see a k in this table? So we have to see how x and y relate to each other. That would mean we're going to have to divide both sides by x to get k. So that tells me if I take all the y values and divide them by all the x values and I get the exact same thing every time, this is direct. Not going to check for that just yet. Because I also know there's a second option. Come on, Blue. And that's the one that is actually the name of this section, inverse variation. Again, I want to see how x and y play with each other. So I'd have to multiply both sides by x. So like I said, this is kind of backwards. The little equation for direct is y equals kx, which uses multiplication. But we're backing up a step and saying, what are we going to see in the table that will tell us it's direct? If you divide, and you get the same thing every time. And then inverse has this little relationship of division. But to see it in the table, you're taking a step back, and it's going to look like multiplication. So, let's get started. I'm going to try for direct over here. For direct variation, if I take y and divide it by x, 15 divided by 2, 7.5 divided by 4, 3 divided by 10, 2 divided by 15, I should get the same thing every time. 15 divided by 2 is 7.5. Wait a second. 7.5 divided by 4? There's no way that's going to come out to be the same number. I'm done checking for direct. It's not working. So let me try inverse variation. Let's see. So this time when I multiply them together, I'm supposed to get the same thing every time. 2 times 15 is 30. 4 times 7.5, that's 30. 10 times 3, that's 30. And 15 times 2, that is also 30. So it came out to be the exact same thing every time. This is inverse variation. Now, it's not enough for me to stop and say, I found it, it's inverse. They want me to write it. But writing these isn't hard. Inverse variation is supposed to be y equals something over x. We just found that something. What was the constant of variation every time? 30. That was the number we need. There it is. So we told them what kind, and we gave them the example. Y equals 30 over x. There it is. Let's go down to B. I'm going to leave this red and blue stuff up here so that you can still see it. Because remember, for direct, even though it's a little equation about multiplication, we're supposed to divide and get the same thing every time. 10 divided by 2, 8 divided by 4, 3 divided by 10. Wait a second. 3 divided by 10, there's no way that's going to come out the same as those. Well, it's not direct. So let's check for inverse. Inverse is about division, so to see it in the table is multiplication. 2 times 10 is 20. 4 times 8 is, oh, Well, if it's not direct and it's not inverse, what is it? Yeah. And that we don't have to write those. It just says, hey, identify it. This isn't going to work. And like I said before, most equations that happen in the real world are neither. They just are. But when we get lucky, we get nice little ones that are going to give us our direct and inverse variation. All right, so let's do the math up here again for direct. X and y have to be together, so we're going to divide both sides here by x so we can look at the table. Inverse, bless you, y equals k over x, but the x's and the y's on the same side actually show multiplication. If you have a calculator, it doesn't have to be a graphing calculator, even if it's a little dollar store calculator, that's going to make this go faster, because I'm going to have you guys tell me, what are you seeing here? So go ahead and check A for both of those, just like we did before. Oh yeah, almost everybody has a phone that does calculator stuff, so could use those too. Anybody find it already for A? Yeah. Direct or inverse? Direct. Direct. So if I do division here, I should see the same thing every time, huh? And what was the same thing? Mm-hmm. So what was the little equation to represent it? Direct variation. Go after B. Looks like just about everybody's found it. Was it direct or inverse? Yep, it was inverse. When you multiplied them together, what'd you get? Now, what I do see is some people are writing these in different forms. Remember, to show that we understand what inverse is, we have to write it as y equals k over x. Keep going with C. What are you putting down for C? Yeah, this is our neither, neither, however you want to say it, but it doesn't work. You try them both ways and it doesn't work. And again, in reality, that's what most situations would be in the real world. We're going to see some nice ones they want us to see so that they actually work, but not everything is as cut and dried as direct and inverse. So now, this says determining an inverse variation. Suppose x and y vary inversely. Ooh, that I stop right there because I write this down. As soon as I see variation, inverse, hey, y equals k over x. Then they give me some numbers. Ooh, that's going to be helpful. When x is 4, y is 12. And I realize I can find k just by multiplying both sides by 4. Now I can write the equation because I know what k is. So this goes back up here. So what function models the inverse variation? That little bugger right there. Y equals 48 over x. Usually there are follow-up questions like C. It says, what is y when x is 10? And if you're wondering, is it that basic? Do I really just put a 10 in for x? Yes, that's what we do. So you could write it as a fraction if you want to, or change it to a decimal. A lot of times with direct and inverse variation, they'll use decimals. But there it is. But here's the big one. What does the graph of this function look like? And for some reason today, I can't even make out any blue lines on these. So away we go. We have this. And we've never seen a hyperbola before, so we don't know what it's going to look like. So we make a table. And I realize I want to pick numbers that would be between negative 10 and 10. So I don't want to use 2, because then it'll be 2 and 24, and I'm not going that high. I just want my negative 10 to 10 window here. 3 and 16, no, that's not going to fit. 4 and 12, no, still too big. 5, 6, ooh, 6 and 8. And 8 and 6, because 48 divided by 6 is 8, and 48 divided by 8 is 6. But I also need to see the negatives. So if I put negative 6 in there, I'll get negative 8. And if I put negative 8 in, I'll get negative 6. See if there's any more. Dividing by 7, no. Dividing by 8, okay, we're already back to our other numbers. So these are the nice ones between negative 10 and 10. Let's graph them. And we've never seen one of these before. So we don't know exactly what to do with that. Because obviously it's not like a line or something. So let me plop it into my graphing calculator and let's see what y equals 48 divided by x looks like. That's what hyperbolas are supposed to look like. Hyperbolas have what are called branches. And as we start, we're going to get nice symmetric branches. So these little buggers here, they do go on forever, but I can't tell that from the numbers I have. So I'm going to change my window. Just kind of like zooming in on this. And now I can really see what's happening. So my hyperbola branch isn't going to touch the x or the y axis ever. Doesn't matter whether or not we're talking about this one in first quadrant or this one in third quadrant. So when I'm drawing this, I have to make sure that it looks like it has a curve and that it's going to get closer and closer to the x and y axis, but it's not going to cross. Now, these are super cool. These are one of those things that if you're into animation, you're into software, writing software for a company, all you have to do is realize how you get these to show up. And I want to show you what happens, because there's some really artistic, cool patterns that you can get with hyperbolas. And that's just by graphing a couple at one time. So you can see how like Southwestern art has a lot of that, the hyperbola type of situations that are going into that, but some very, very cool artistic things you can do. In fact, in college, you've got hyperbolic functions 1, 2, and 3. I mean, there's whole fields of math on hyperbolic functions. So very, very cool artistically. Let's do another. Suppose x and y vary inversely. Oh, stop reading. Vary inversely. Y equals k over x. X equals 8 when y is negative 7. Find me k, please. What's k? What did you get for k? Let's put it in there. And think of some good numbers while I'm trying to get these little blue lines to show up. Good numbers for negative 56. Yeah, why not, right? So here's what's a little bit different about this one. Because we'll have two negatives, if I put negative 8 in, I'm actually going to get a positive 7. And if I put negative 7 in, I'll actually get positive 8. Well, I want a couple more. So I think, well, what would happen if I do put the positives in? So if I put a 7 in and an 8 in. Well, if you put a 7 in, you get negative 8. And if you put an 8 in, you get negative 7. We're still going to see the two branches. So let's graph them. We've got 7 and negative 8. 8 and negative 7. Negative 8 and 7. And negative 7 and 8. Wait a minute. Those aren't showing up in the right quadrants. This one we graphed up here before was in quadrants 1 and 3. Remember, it goes counterclockwise. 1, 2, 3, 4. 1 and 3. What do you suppose made this one go into quadrants 2 and 4? And a negative, yeah. And a negative. So instead of quadrants 1 and 3, this one went in 2 and 4. Still a hyperbola. C says, what do you do if x equals 2? Don't overthink it. You plug it in. Y equals negative 56 divided by 2. What do you get? It is. All right, we got it. So direct and inverse, not that tough, right? So now we're going to go to the word problems knowing this is not that tough. It's not that bad. All right, look at that label up there, modeling variation. Of course, that's what we've been doing today. Oh, you guys are the best. Your math class has decided to pick up litter each weekend in a local park. Oh, wow. Service-oriented, love it. Each week there's approximately the same amount of litter. That's depressing. people have to see out there. Don't they start picking up after themselves? No. The table shows the number of students who worked each of the first 4 weeks of the project and the time needed for the pickup. I don't want to have to check for direct and inverse if I don't have to. I want to think through this. So, as I get more people to help, will it take a longer amount of time or a shorter amount of time? So as one goes up, the other goes down. This should be inverse. Should be. So let's check it out. Let's put the x and the y on one side. And let's see. If you take 3 times 85, do you get 5 times 51, 12 times 21, 17 times 15? All right, let's check these numbers out. Bummer. They're not all the same. Are they close enough? Do you believe that it's possible that with different people, it might take a little bit longer to pick up the trash on some days? A little bit less time. Of course. Overwhelmingly, it looks like 255's our go-to, right? So if for some reason we had somebody that was really, really fast at picking up trash and, the other one got to be 252, but let's stick with the 255. I mean, that's real life. Somebody's faster than everybody else. They want to get out. Now, they did say we shouldn't use x and y, so let's fix it. They said use n and t. Because here comes the important part. I am certain that each week people would take turns figuring out who it is that's going to get everybody together to go out there. And what you find out is this. When you call people and say, oh, I only have 3 people, it'll just take us an hour. Well, all of a sudden 3 people say, I'm not doing this. This is an hour. So if you get more people, then you can say, hey, 30 minutes max. That's it. Well, how many people? I mean, if you're in charge of it. So let's take our 30 minutes and put it in for T. And let's see how many people you'd call and confirm are going to do this so that you could get it 30 minutes or under. Well, we can't have 8.5 people. Can you round down? Because then you wouldn't do it in 30 minutes or less, right? We'll have to go with 9. 9 peeps out there picking up garbage. Well, I was proud of the fact that you wanted to pick up garbage. Now I'm really proud of you. After a major storm, your math class volunteers to remove debris from yards. Of course you do. It's just the kind of people you are. The table shows the time T in minutes it takes a group of N students to remove the debris from an average-sized yard. Are we in agreement? The more people we have, the shorter amount of time it will take. All right, so it's inverse again. And let's figure out K. Uh-oh, I didn't move it far enough down so I could still see it. There we go. Oh, well, I'll punch it in just because I want you to be able to see them all, but we all know 225 times 1 is 225. Probably know that one too. Are we okay with that? It's real life. Stuff happens. What would you use for K? Me too. 3 of them were 225. Let's just use 225. But again, they're not using X and Y. Let's put the N and T back in there. Because they want N to stand for number of people, T to be time, make it really easy to use. So we already took care of A. What function models the time needed to clear the debris from an average side yard relative to the number of students who do the work? Got it. B. 30 minutes was too long. You had a couple people drop out. So now you want 25 minutes to be your max. Where are you putting the 25? Yep. 9 people again. I wish they would have changed that, but you know, the numbers are what the numbers are. Your data sometimes ends up being close to the same. So there it is. Were those difficult? No. All right, so help me out here so that I know you've got this. Give me the generic equation for direct variation. Y equals kx. Good. K times x. What's the generic little equation that we have for inverse? Y equals k divided by x. Superb. I'm going to get you some graph paper because there are some of those that you need to graph, those little baby hyperbolae.